Sorry about that, guys. So we missed a little bit, not too much. All right, so as we are increasing the adding heat or energy to the system, temperature goes up, but on the flow up, we have a solid line. Okay, it's still solid, I should say, till we hit that first plateau. And this could be 0 degrees. We're talking about water here. At 0 degrees, we got the first plateau. And at this point on the plateau, it is where the solid is being converted to liquid. And so we have a very structured, solid ice cube, okay? And that's supposed to kind of represent structured, solid ice cube. And then as we put energy into the system, we are breaking the IMF interaction between the molecules, such that as we break them apart, the molecules start to move away from each other. That force, IMF force, is not as strong with each other anymore because we got energy into the system. And now they go into the liquid phase, where now the molecules are kind of like in random all over the place. They can move around. That is structured and ordered as in the solid phase. So on the first plateau, the solid, there's a conversion of the solid to the liquid. When all of the solid has been converted to liquid, guess what? We have another rise in temperature. And on that rise, it's all liquid until we hit the second plateau. And since we're talking about water, that second plateau will be 100 degrees Celsius. Okay, second plateau. On the second plateau, the liquid now is being converted, moved to the gas phase. And so now where we had, somewhat ordered looking molecules, were being converted to gas molecules where they're all separated quite a bit. Note again, the plateau. As we add heat, there's no increase in temperature because all the energy on these two plateaus that you're putting into the system is being absorbed by the molecule, so it breaks up the IMF interaction, okay? So the next time you're out there boiling a pot of water for some spaghetti, okay, and someone tells you, if it's boiling and someone asks you to turn up the heat, it's not gonna save your money on electricity or gas, because no matter what you do, that temperature is not gonna get any greater than 100 degrees if you're boiling water. It's gonna maintain at 100 degrees until that time that all that water in the pot is boiled away and converted into the gas phase. Then your temperature will go up, okay? So save your money. And once your water is boiling, leave it at that temperature, or even kick it back a little bit, save some money there. All right, so on these plateaus, what is happening there is the energy is being absorbed to break up the IMF interactions. And obviously, I hope you can see here that depending on the type of force, if it's a real weak London force, then that temperature is going to be way down, much lower as compared. This is an example of hydrogen bridging. And then obviously, dipole forces would be much lower, okay? So, for example, we have water, like I said, is 100 degrees Celsius for boiling point, and if you look at, say, ethanol, good old-fashioned drinking alcohol, ethanol, that boiling point is about 78 degrees. So that would infer that the intermolecular forces for ethanol are much less than for water. And even though ethanol still has hydrogen bridging forces, okay, because there's some other forces occurring for ethanol that reduce its boiling point. All right, so the takeaway from here is during these phase changes, the temperatures remain constant, and all the energy that is being put into the system is being utilized to break up the IMF, okay? Now, the important thing is you're not breaking bonds. It's important. When you heat something, when you heat water, you're not breaking the bond of H2O, the hydrogen-oxygen bond. You're not. You're breaking IMF interactions. Okay. To break the bonds, it takes a heck of a lot more energy than just heating it with given the temperature. All right. That, ladies and gentlemen, is the end of chapter 14. Okay. Any questions about that? Those of you that came in late, let me share something with you. I'm going to jump into chapter 15, which is basically like 15 slides, much less. So it's going to be another quick one. But let me share the what we have left over time-wise. Okay. Today's the 26th. Obviously, we'll finish chapter 15 today. Thursday, I will be here. Now, I'm on the clock, so to speak, so I'll be here from 4 to 4:15. Obviously, we'll be done with all the chapters, unless we don't finish with 15 today, then I might have to carry over to Thursday, but I don't think that'll be the case. But again, that day will be open for a study day. Come in for any questions you may have for the next exam coming up, which is the following Tuesday, on the 3rd. That's exam number 5. Okay. A week from the 3rd, which is the 10th, is the final exam. Okay. So you have time, if needed, starting this Thursday, the 28th. And then I'll be here on the 3rd, I'll be here on the 5th, and I'll probably be here on the 10th for an hour or so if necessary. If needed, or more time if you need that, no questions, because you need to, if you have any questions about the finals or any of the chapters, that's your opportunity to come in those days, okay? And then the 12th is the last day to turn anything in, because Canvas will shut you off. So if you have any missing assignments, that's your last opportunity to knock it out. All right, any questions about that? So you know where we're at. So I'll be here the 28th, on the 3rd, the 5th, and the 10th. Okay. I won't be here the 13th, the 12th, because we're officially done on the 10th. All right. Any questions about that?
No questions for me.
All righty. Sounds good. All right. So this brings us to the last chapter that deals with solutions. We're going to talk about making coffee. No, I'm just kidding. It is a solution. And what we're going to talk about is different types of solutions. But first, let's define what a solution is, okay? A solution is defined as a solute dissolved in some solvent. But bear in mind, there is not necessarily liquids. And so I'm going to push to change this definition, because basically it's a material mixed in with, in a certain concentration, mixed in with another material in a much higher concentration. That really encompasses all the possible types of solutions that we can have, because most of the time people think of solutions as being solvents, and that's not always the case. Okay, because the solute is generally the chemical that's present in the smaller amount, and the solvent is the chemical present in a larger amount. Now, most of the time we're talking about water, and so it's an aqueous system, but it doesn't have to be that. It could be a solvent, it could be solids, okay? It could be gases, it could be a different combinations of things, okay? For example, well, I don't want to go there yet. So concentration, this is pretty self-explanatory, right? We have concentrated solutions and we have dilute solutions. And so if you look at this, it looks like a glass of Kool-Aid. You know, obviously in the far left, you have less of the solute, okay? On the far right, you have more of the solute, and therefore you have a stronger color. So by looking at this, you can see, hey, the one on the left is pretty diluted compared to the one on the right. And this particular property, we can actually use this when we want to measure color solutions. We run into a special instrument called the spectrophotometer that we can measure the intensity of color of, say, a standard solution of these 5 different, if we know the concentration of these 5 glasses, put them in the instrument, we can create a graph. So now you can take any unknown color of this material, put it in the machine and then run it on the graph, and you can actually determine the concentration of the unknown, okay? All right, so examples of solutions. Well, one example is you can have gas in the liquid. Here you have a solvent, but you can have a gas. Typical example is like a carbonated drink, like a soda, okay? You can have liquid in liquid. Classic example is a mixed drink where you got, in this case, vodka and tonic, okay, rum and coke, whatever you like there. It's 2 liquids and that make a solution, okay? You can have a solid put into a liquid. So if you, obviously, I'm sure you know, you can take some sodium chloride, table salt, and take some water, and it will dissolve. You have salt water, okay? So you can make a solution. And if you add more salt, obviously, you make it more concentrated, okay? But there is a limit when it comes to dissolving things. There is a limit of, even though something is soluble, I mean, it makes sense if you think about it. If I have 1 teaspoon of salt and I have a gallon of water, you know, it's gonna dissolve. But if I have a teaspoon of salt and I have a teaspoon of water, it's not gonna dissolve very well, right? So, you know, there are limitations to solutions. Another example of solutions is gas in the gas, where here's a solution. We have a mixture of gases, okay? And then we can have solid in the solid combination. A good example would be the alloys of different metals. Steel, for example, is not just iron by itself. Iron, 100% iron, would not function as a tool to use in buildings because it is in itself very soft metal. So what is done is things like carbon and other elements are put into it, mixed into it to make alloys to give it strength. Other examples would be the gold that you have in jewelry. Very rarely would you find 100% gold as being used to make jewelry like rings and so forth, because pure 100% gold is very soft and be kind of tough. Well, it wouldn't be very safe to make a ring out of it, especially if you smash your ring, you smash your fingers. Brass is a mixture of copper and zinc, okay? And we have, you know, just hundreds and not thousands of different alloys that give different properties. All right, now, we mentioned this before, it's related to polarity, okay? The rule is like dissolves like, meaning that polar solutes will dissolve in polar solvents. Yes, there's degrees of solubility, but as a general guideline, if I have a polar solute, I will need a polar solvent to make a solution out of it. The converse is also true, that nonpolar solutes will dissolve in nonpolar solvents. We all know that water and oil do not mix. Water is very polar. Oil is very nonpolar. They do not mix very well, okay? And here's a classic example. Nonpolar and polar do not mix, okay? Now, with respect to when we talk about whether things will mix, we use a term either as miscible or soluble. The difference is this: the term miscible deals when you're dealing with two liquids. If two liquids mix, then we call them miscible. If they mix because they're both polar, they're miscible. If they mix because they're both nonpolar, it's miscible. If they don't mix because of difference in polarity, it is immiscible. Okay? Immiscible. Now, with respect to solids in liquids, if the solid obviously dissolves in a solvent, is the term to use is soluble or insoluble. Now, when we are dealing with aqueous systems, obviously we utilize the solubility rules to determine whether a solid material is soluble or not. All right, so we have a table here, and they're asking you to determine which solutes dissolve in which solvents. Okay, what can you predict? Is basically, can I predict that? And the answer is yes. I first need to determine the polarity of everybody. Okay, and to determine the polarity, I need to recognize a number of things. One, if I need to, I use the Lewis-Dot structure, so I can draw the geometry, which will give me information as to the polarity, overall polarity of the molecule. Okay, because remember, sometimes you may have polar bonds, but if they cancel out, if the polar bonds cancel out, then the molecule is nonpolar. If you have polar bonds and they do not cancel out, then you have polar molecule. If you have all nonpolar bonds in the molecule, then you end up with a nonpolar molecule, okay? And recall that the carbon-hydrogen was considered a nonpolar bond. So let's take a look at the solvents here, okay? We did ammonia already, okay? Ammonia had the lone pair on the nitrogen, and we determined that it is polar in nature. But the next one is the C12H26. Now, you may not know what that is, but that's okay. But I hope at this point in time that you recognize that you are dealing with carbon and hydrogen. Let me change the color here for a second. That you are dealing with a molecule that has nothing in it but carbon and hydrogen. Okay, carbon and hydrogen bonds, which should tell you that I'm dealing with a nonpolar bond. Okay, this is a carbon molecule. Something unique about carbon is they tend to bond with each other very readily, and you can make long chain hydrocarbons. So what you got here is one example. You got 12 carbons bonded to each other. In fact, a lot of fatty acids, for example, have 12 carbons. On one end of the fatty acid is a long hydrocarbon chain, and on the other side of the fatty acid is a polar side. A lot of our soaps and detergents have that property where they have a polar side and a non-polar side. And so they function to clean you up, either soaps to clean your clothes or yourself, is the non-polar side will dissolve the oils and so forth, and then the polar side will interact with water to be washed through. Okay, so this guy here, C12H26, recognized that you had nothing but carbon and hydrogen, therefore I have a nonpolar species. And then bromine is diatomic, two atoms, they're the same. Automatically, I got a nonpolar solvent here, okay? We then look at the solutes. We got HCl. We did talk at length about hydrochloric acid. That is very polar. Again, by the same reasoning for I2 and bromine 2 and the diatomic, it is nonpolar. Okay, diatomic, being nonpolar. PCl3, you might have a little more of a challenge with that. So, but if you do, Lewis-Dot structure, okay? Remember the Lewis-Dot structure? And when you do that, you'll find that you have the following. Phosphorus is the central atom. You'll end up with this type of Lewis-Dot structure, okay? And the general guideline, as I mentioned, was this. I said, whenever you end up with a lone pair in the central atom, automatically can think of polar species. But if you forget that, remember something else. Remember that, yes, we got a polar bond here, 3 of them, okay? And you might think, well, okay, I got 3, I could have a tetrahedral configuration, but, and being, if you have these in the tetrahedral configuration, the polar bonds will cancel out. However, remember I get the lone pair, and the lone pair takes up a lot more space. Therefore, they push the phosphorus chloride bonds to each other and shrink that bond angle here, okay, to much less than 109.5, resulting in these bonds not canceling out, okay? The result being is that we have a polar solute. Then the last one, CH4, same reasoning we just came up with the C12H26, made up of nothing but carbon and hydrogen. Then we have a nonpolar species. Okay. Now, once you define the polarity of the solute and the solvent, now you can determine whether they will dissolve in each other. Bearing in mind, remembering that like dissolves like, okay? Like dissolves like. So yes, for the first combination of ammonia and hydrochloric acid, because they both are polar. No for the next combination, because we got a nonpolar and a polar species. Yes for PCl3, and obviously no for the CH4 methane. That is methane, by the way, CH4. No for the next combination, because we got a combination of the nonpolar and polar. Definitely yes for iodine. No for PCl3 because the differences in polarity. And yes for methane, okay? Again, because the same polarity. No for bromine and HCl. Yes for that bromine and iodine combination. No for the bromine and PCl3 combination because the differences in polarity. And yes for the last one. Excuse me. All right. Now, when it comes to the liquid solid combination, we have a polar liquid, polar solvent. That would be classified as miscible combination, whereas immiscible for a nonpolar solvent. Nonpolar liquid, polar solvent, immiscible, miscible for both being nonpolar liquids, okay? We use the term solid when we're dealing with a liquid solvent and a solid. Okay, the solute is solid, so we have a polar solid and a polar solvent. That would be a soluble species, okay? Polar solid, nonpolar solvent would be insoluble. So insoluble for nonpolar solid and polar solvent. Soluble for the nonpolar solvent. Ionic compound, like let's say sodium chloride, well, polar solvent, we have to check. When we do polar solvent, most of the time, if you're dealing with an aqueous system, and then we check with the solubility rules, okay? Whether it's soluble or insoluble. And definitely insoluble if you got an ionic compound and a nonpolar solvent. I'm sure you maybe have tried this. Maybe you're cooking some eggs at home with a little oil, and you maybe throw some salt in there. The salt just stays, it doesn't dissolve, okay? Because there's the differences in polarity. All right. So we talked about this before, where we had the dissolving process, where we had the sodium that was being solvated with the water molecules, because remember, the water molecules have this partial negative. We got a full positive on the ion, and so therefore there's a strong interaction. This is an ion dipole interaction, okay, going on here, okay, between the sodium ion and the partial negative of water. There's actually 2 partial negatives on water. And then in the other side, we have the chloride. If this was chloride, for example, If it was, then we have the interaction, but it'd be whatever anion that sodium was associated with, we'll have that interaction going on, okay? All right, so we're going to talk about concentration. And then we'll be done very quick. All right, we have two units for concentration. We have what is called a mass percent, okay, which is a ratio of weight, mass percent times 100 to give us a mass percent. All right, you may be familiar with it. There's a lot of alcohols like beer, 2%, 5%. They deal with a weight ratio. They even deal with a volume or a weight volume combination. Okay, and more is said on that in a bit. And then we deal with molarity. We did talk about molarity when we were talking about the pH. Remember, we had the H of the proton, then we put it in the bracket. We said that was the concentration, which was defined as the moles of that material divided by the volume is dissolved in liters. So the ratio is moles over liters. So the fact that we need moles, we thought you got away from this, so we have no more moles, well, they're back. Okay. The fact that you need moles should tell you, you know what, I also may need the molar mass. Okay. The molar mass, because remember, molar mass has the units of grams per mole. Okay, and so to get the molar mass, what do we need? We need to find the formula to determine the formula of the molecule. And occasionally, we talked about to write the formula. What did we say? I talked about write them first in ion form. If you're dealing with ionic compounds, form. Write the ion first, and then that way you can determine how many of each you need to add to make sure when you put them together that you have the right amount of each of the ions. And once you have the formula, then you can tally up how many elements of each species times their respective atomic weights, tally that up, and gives you the molar mass, okay? All right, we'll do an example or two of that. Now, mass percent, how that is defined. It is defined as follows. It is defined as the mass of the solute divided by the mass of the solution. Now, the thing that sometimes students forget is the mass of the solution is not only the mass of the solvent, but is the mass of the solute, okay? Let me repeat that. The mass of the solution, because remember the solution is made up of a solute and a solvent, okay? So the mass of the whole solution incorporates the mass of the solute plus the mass of the solvent, okay? And so let's take this example here where they say, calculate the mass percent if you take 15 grams of potassium nitrate and you dissolve it in 135 grams of water. Okay, point number one. We are talking about the mass percent. Therefore, we don't need to know the formula for potassium nitrate. It could have been any compound. Okay, all we need to know is how much of that compound is being weighed out and how much of the water is being utilized. That's all we need to know. So we don't need molar mass. We don't need it doesn't play a role. We're just looking at the weights for that solute and the weight of the solvent. And so we plug it in, it's 15 divided by 15 plus 135 times 100. That means that if I take 15 grams of potassium nitrate and I dissolve it in 135 grams of water, I will have a 10% solution. Okay, that is a 10% solution by mass. Okay. And sometimes you might see it by volume if they talk about, if they're liquids, your volume of the solute and the volume of the solution. You use the same type of calculation here. All right. Another place you may have seen, for those of you that maybe have work in the medical field, you may have heard or see even on TV, they say get a saline solution. You're at the hospital and they want to use a saline solution. Well, saline is nothing more but sodium chloride in water. Okay. But it is specifically a 0.09% solution. It's very specific because that keeps the osmotic pressure fairly uniform. So if you just take pure water or just something that's over concentrated with salt, you can end up destroying your cells. Okay, so very important solution in the health industry, our health, especially if you got an IV or something. All right, so and you calculate it the same way. Now, occasionally, notice here we've been given the mass of the water, okay? You've been given the mass of water, but it is feasible that the mass of the water could be an unknown, okay? You know the mass of the solute, you know what percentage you're trying to make, so they want you to calculate, well, how much water do I need if I use this amount of solute to give me this percentage of solution, okay? And so this is the only time that you're probably going to need to use a little bit of algebra. Not too complicated, but just a little bit. Now, here they're asking you to calculate the amount, how much grams of water are needed to make a 5% solution if you use 10 grams of salt. And salt can be anything, okay? Because we're doing mass percent, don't really care about what specific salt we're using. All right, so we set the problem up, okay? What we don't know is the amount of water, which by definition is for mass percent is the mass of the solvent. And we don't know what it is, so we can substitute an X for it, so we end up with this algebraic equation. We need to solve for X. Now, we can solve, I used to teach algebra in Carrington College, and what I would tell the physical therapy students there is algebra, you can have 2 or 3 different ways to solve the algebraic equation. Not one way is correct, okay? But if you end up with the same, you can end up with the same answer by solving it a couple of different directions. So what I'm going to do is I'm going to follow the textbook, and now I'll add some alternative ways that you could have solved for X if you want. All right. So what they did here is they end up with this following equation. You might ask, well, how did they do that? But to refresh your memory, what they did is they took the quantity 10 plus X and multiplied both sides of the equation, okay? That results in this canceling out, having 10 times 100 left over and moving that 10 plus X to the left side of the equation, okay? All right, that's one way to do it. One can actually multiply 110 and then go a different route, but that's okay. This is one way to do it. Now you end up with this. Now, what they do next is they end up with this. Well, no big deal. What they did was just multiply 100 times 10 to give 1,000. All right, next step is they ended up with this. Well, what they do here? Well, they took the left side and divided by 5. And as you know, what you do to the left side, you got to do to the right, vice versa. And so 5's canceled here, leaving us with 1,000 divided by 5, leaving us with 10 plus x equal to 1,000 divided by 5. That is one way to do it. Alternatively, you could extend this, multiply 5 times 10, 5 plus x, okay, and then you end up with another equation, and you can solve for x that way. 6, 1/2 dozen the other, you're going to eventually get to the same spot. Now at this point, what they do is they go ahead and take 1,000 divided by 5. They end up with 10 plus x equals 200. Now you're almost there. You want to solve for x. So you subtract 10 from both sides. 10 cancels, so now you got x is equal to 190. Okay. Now, all right. Now they write it in scientific notation because of sig figs. Okay. Now your question is, well, if you write the answer 190, 190, you don't have sufficient number of sig figs because you start off with 5.00, which is a measurement of 5%, which is 3 sig figs and so forth. And you have 10.0 grams, which is 3 sig figs. All right, so you need your answer in 3 sig figs format, and writing it as 190 would want to give you 2 sig figs. All right, so the question at this point is, well, how do I know if 190 is correct? Well, quite simple. You take your answer and you plug it in back into the equation you set that up. Okay, and do the math. And what you should do is you find at the end that 5.0 will equal 5.00, which is a true statement. 5 does equal 5. If for some reason you come up with something other than 5, then probably check your math up here, or the 190 is incorrect. Go back and check your algebra. Okay. All right. Right, that just verifies that that's the answer. So we have 2 examples here of how to calculate the mass percent of the solution. Straightforward. Second example is, well, how do I calculate the amount of water I need if I start off with X amount of salt? We just did that example. I've been asked, well, what if would I ever need to calculate the amount of salt that I'm going to need to use? And the answer is yes, but you won't find that in any of the questions. It's either going to calculate the amount of water or just calculate straightforward the mass percent. Okay. All right, which brings us to the last concentration, which is molarity. Okay, as I stated earlier, it is defined as the moles of solute divided by the liters of solution. Now, keep in mind, the units have to be in liters. So if you're given if you're given the volume in milliliters, you got to convert that to liters, right? Remember that there are, in 1 liter, there are 1,000 milliliters. That's your conversion factor. Right, calculate the molarity if 9.99 grams of potassium bromide is dissolved in water. Okay, now, what I need to do is first I need to determine the formula for potassium bromide, okay? Because without knowing the correct formula, I will not know the correct molar mass. I need to know the molar mass. Why? Because I'm given 9.9 grams of potassium bromide, and I need to calculate the molarity, which tells me I need to calculate the moles of potassium bromide. So first things first, I got to write the formula. So potassium bromide, ionic compound. So let's write them into ions first. What I know about potassium, potassium is a group 1 metal. And when in ionic form, being a group 1 metal, it will have a +1 charge. Bromide is a group 7, a nonmetal, okay? And it gained 1 electron because it's a group 7. And each one has room for 1 more electron. It's a nonmetal, it would gain electrons. So those are the ions that are the factor here. Now I got to put them together with the correct number of each to cancel out the charges. And fortunately, it's a simple 1-to-1. It's simply a KBr. Okay. So now I got the formula. I look up the atomic weights for bromine, atomic weights for potassium, and that gives me the molar mass. That being said, I got the molar mass of 119.00 grams per mole. Remember, the atomic and the molar mass is a ratio of grams per mole. I start off with grams. I want to go to moles, so I divide by the molar mass. Okay, check my units here. So notice that my grams cancel, leaving me with units of moles. All right. Now notice here's a bunch of numbers here. Now, when you do the first part of the math to calculate the moles, you know full well you got 3 sig figs here, and your volume has 3 sig figs. So the ultimate answer should have 3 sig figs. Okay. However, don't truncate anything until you're done at the end. So carry out the moles as far as you can, way over the 3 sig fig digits. Okay. And then divide it by the volume. So obviously the volume here is already in liters, so we can simply divide it. 0.08395 divided by 2.5 liters. The molarity of a solution of potassium bromide containing 9.9 grams of potassium bromide and 2.5 liters of solution, its molarity is equal to 0.0336. Okay. All right. Let me rehash here. All right. So you're given the weight of your compound. The compound is given in the name. You need to write the formula to give you the molar mass. So you write the formula in ionic form, so you can put it together properly. Okay, that gives you the molar mass. So you take the weight you're given, divided by the molar mass, gives you the moles of your solute. And then in this case here, then we divide that by the volume, and the volume has to be in liters already. So we don't have to convert that anymore. So we just simply do the math, keeping track of your sig figs. Okay. All right, yeah, do work the practice sheets. There are some examples in there for you to do. All right, let's take this one. We have calculate molarity if you have 5.0 grams of sodium phosphate and you dissolve it in 255 milliliters. All right, point number 1, your volume is in milliliters, okay? 255 milliliters. You need to convert that to liters. So one conversion factor I'm going to need is 1 liter is equal to 1,000 milliliters. Okay. We're given 5 grams of potassium phosphate. Well, we need the molar mass. We're in grams, and we've got to get to moles. Okay. Keeping in mind that the units you're looking for are moles per liters. Okay. So, but we need to figure out the formula. So we need to figure out what sodium phosphate is all about here. The fact that you got phosphate, ATE, hopefully should, at this point in time, should say, hey, let me go to the periodic table, because it sure sounds like a polyatomic ion. And once you do that, you will find that its formula is given to you as PO4 -3. That is the charge of the phosphate polyatomic ion. Sodium, like potassium, is a group 1 metal, and therefore it would have a +1 charge when it becomes ionic. Okay, So those are the ions we're working with. We're going to make sure we put enough of each. I'm going to need 3 sodiums per 1 phosphate, okay? So the formula for sodium phosphate is Na3PO4. Okay. Now that I know this, I know the formula, now I can do the molar mass. I got 3 sodiums, 1 phosphorus, and 4 oxygens. Go to the periodic table, look up the what do you call it, the atomic weight for each one, tally it up, and you should end up with a atomic weight of 163.94 grams. Okay, its molar mass is 163.94 grams per mole. And just like the previous example, we're taking 5 grams of sodium phosphate. We're going to divide it by the molar mass, and then we're going to have this long number here that we want to keep the long number because we don't want to truncate. The thing about truncating beforehand is you propagate your error in your final answer. So don't do that. Wait till you're done with all the math and then truncate at the proper sig figs. Keep track of your sig figs. Notice something. The 255 has 3 sig figs and the 5.0 has 2 sig figs. So your answer should only have 2 sig figs at the end, okay? All right, so now we take the 255 divided by 1,000. That gives us the volume in liters. Now we can go back and plug in the numbers, and you end up with, clear the mess up a little bit here. You end up with a molarity for sodium phosphate of 0.12. So if I take 5 grams of sodium phosphate and I dissolve it to exactly 255 milliliters of solution, its molarity for that solution will be 0.12 moles per liter, okay? All right. All right, so don't forget the assignments, all right, that you may need to catch up on, and there is a practice final exam on the website, so do use that as a resource. There's also other final exams, old ones that were put on the website that you can take a look at. Those were made for when we were doing on-campus classes, but the questions are the same. They've just been converted to fit in the format of Canvas. So very similar. I shouldn't say the same. They're very similar. Okay, but it does give you an idea of what type of questions you can anticipate. All right. Congratulations. You are done with 15 chapters of chemistry. We did pretty well scheduled.